The next learning objective in the standard of momentum is about calculating the vector sum of momenta for multiple objects in a system. So we need to understand what momentum is to understand this learning objective. So momentum is defined simply as the product of an object's mass and velocity. That's it. If you do a Google search for definition of momentum, you're basically going to get the same thing. By definition, it is just mass times velocity. Now, momentum is typically indicated with a lowercase p, and for this problem, I have drawn the arrow above the momentum and the velocity. That arrow there indicates a vector. So momentum is a vector quantity. Mass is a scalar quantity, doesn't have a direction, and velocity is a vector quantity because it has a direction. You can multiply a mass times a vector, and that is just fine. It just makes the vector bigger or smaller. That's all. Momentum has a magnitude and a direction, and the direction is the same as the velocity because the mass doesn't change the direction it's going. That kind of makes sense. The mass wouldn't affect where something is going. It's just affecting how much momentum is behind it. Let's take a look at an example. This is a really simple one. Here we're just going to be applying this equation. So we have the momentum is equal to the mass times the velocity. So momentum is equal to, and I'm going to keep the vector notation for right now. We have 3 kilograms mass, and then we're going to multiply by the velocity. Since this is a one-dimensional problem, what we could do is instead of drawing the vector symbol, let's just put a little x down here. So this is the momentum specifically in the x direction. And then we can not have to worry about the vector notation for the velocity. We could just use positive or negative. And this problem hasn't defined what positive or negative is yet, but we can probably safely say that to the right is positive and to the left is negative. So we have 3 kilograms times the velocity of 5 meters per second, a positive 5 meters per second because we made to the right positive. And that gives us a momentum of 15. And now let's talk about the units. So you could say that this has units of kilograms, meters per second. That would be valid units for this. You could also multiply by a fraction which is seconds over seconds. And you might be thinking, why in the world would we do that? Well, if we do that, a kilogram times a meter divided by, on the bottom, we would have seconds times seconds, which is seconds squared. And then we'd still be multiplying by seconds. This little bit right here should look very familiar. This is a Newton. So it turns out that the units for momentum could be kilograms times meter per second, or it could be a Newton times a second. In future learning objectives, we'll get to why that is super important. The previous one, kilogram times meter per second, gives us a clue about what momentum is in terms of the equation. We have a mass unit and we have a velocity unit. So we have a mass unit times a velocity unit. So it's probably some kind of mass times some kind of velocity. Sure enough, that's what the equation is, mass times velocity. Let's apply this to a slightly harder problem. Now, here we're just going to have multiple objects, which if we remember the learning objective was about that we can have multiple objects. So we're going to calculate the momentum of each of these objects and add them together because what we're looking for is the sum of momenta. And we have on the left-hand side, we have a 10 kilogram mass going a positive 5 meters a second. And on the right-hand side, we have a 20 kilogram mass going a negative 3 meters a second. This symbol right here we've seen before with Newton's second law. This is our good old friend sigma, which just indicates the sum of all. So what we're doing is we're adding up all of the momentum. Eventually in your math classes, you'll learn a more advanced notation for sigma, which I'm going to show you right here. And that's going to involve this I equals 1 or I equals 0 or potentially n equals 1, n equals 0, and a number on the top. What this is indicating is this I equals 1. That is saying, okay, start with 1. Start with this value right here, this little subscript I, have it start with 1. So let's go ahead and do that. Let's go ahead and write M1. So we just replace the I with 1, V1. Then the number on the top here is indicating what number you're going to go to, and you're going to hit all the numbers in between, all the whole numbers, the integers in between. Now, there is no whole number integer between 1 and 2, so we're going to have our last one, which is 2. So this is m2 v2. This is powerful in math class because this number on the top could be 100, and it's a lot simpler to write this notation right here than to write out this, but 100 times. So it's a more compact way of doing that. In computer programming, for any of those that have done any computer programming, this symbol right here is essentially a loop. You are looping over I equals 1 to 2, looping over and adding these two things multiplied together. Once again, since we are working in one dimension and one dimension only, we're going to drop the vector notation from now on. And we could include a subscript showing that it's in the x direction, but we're not even going to include that. We're going to simplify this down to just one-dimensional, so we're going to drop all the subscripts except 1 and 2 for objects 1 and 2. So let's write this down here again. The sum of all momentum equals m1v1 plus m2v2. Let's plug in some values now. So for m1, we have 10 kilograms. For v1, we have 5 meters a second. And then we're going to add m2, which is 20 kilograms, times a negative 3 meters a second. And that right there, this little negative sign, is the most common mistake students make. Students often forget to put the negative in there. They often forget to assign the negative value because it's going in the opposite direction. Here, the problem was already set up and it showed the negative. But if you were just told one object is going one way and one object is going another, students might often miss the fact that you needed to set one of those velocities to be negative, or this wouldn't work. Well, let's finish this problem out. So what we have is 50, and we'll go with this unit arrangement, kilogram times meter per second, plus, well, not actually a plus, let's bring that negative out, minus 60 kilograms times meter per second. That's going to get us a negative 10 kilograms times meter per second. So the sum of all momentum is equal to negative 10 kilogram times meter per second. So the overall momentum of the entire system, so if you include all the objects, the overall momentum is to the left. So this is the sum of all momentum, and it's to the left going at a negative 10 meters per second. 10 kilograms meters per second. That is the sum of all momentum, the total momentum. So the entire system has a net momentum to the left. I've done one simple practice problem showing you how to just apply the equation of P equals mv, or momentum equals mass times velocity, and then we applied it to having multiple objects, and you showed you how that worked. By the way, if you had more than 2 objects, you would just add another term, and you would just keep going into however many terms you have. You could have 4, 5, 6 terms. You could have 7 objects and have 7 terms. It doesn't have a limit. For your practice, you're going to be doing exactly what I did in the second example, except this time there are going to be 3 objects. Not any more difficult, just a little bit more tedious.